Welcome. Today I have been rounding up the list of things that I have discovered while going through the universe of the ellipse. And there are some interesting things that I think are worth note. First of all is this fudge factor, the letter K, that we introduced into the formula that we use to calculate the surface area and later on the perimeter of the ellipse. If you recall, we did some experiments and found the interesting thing about K is that it is a function of A and B, first of all, and secondly, when the ratio of A to B is calculated, whenever the value comes out the same for that ratio, K will have the same value as well. So when K has been developed from A equals n times B, where n is any integer, you find that K will have the same value for any pair of semi-major axes and semi-minor axes ratio that has the same value. So to make that clearer than my explanation, I'm going to look at a table here and show the discovery that not only did we have K being the same value when the semi-major axis is twice the semi-minor axis, but it also has the same value when it is 3 times the semi-minor axis, when the semi-major axis is 4 times the semi-minor axis. So at any multiple of the semi-minor axis, K will repeat the same value. So let's see it in the table. We have 9, which is 3 times the semi-minor axis, 3. And when we look at K, it'd be 1.508 and some other numbers. And then we go back, and here is 18, which is 3 times 6. And we get the same value, 1.508, 06615. Going on, we have 6, which is 3 times 2. And once again, the same value, 1.508066615. We have 12, which is 3 times 4, 1.508066615 for K. The same value. I don't know how many times I did this. 75, which is 3 times 25. And K again repeats. 105, which is 3 times 35. K again repeats. So I said, okay, 2, 3, that's good. Let's try for 4. So I went for 4. Here is 12, which is 4 times 3. We get 1.8636399973. And now 16, which is 4 times 4. And it repeats again. So I figured there was no need to do as many examples because the pattern is clear. Went on to 5. 30, which is 5 times 6. 2.235324702 for K. And obviously 5 is 5 times 1. And again, once again, K gives the same value. Say, okay, well, we've got it for whole numbers, integers. Now let's see if it can do real numbers. So I went for something in the real number system. So here's 7.5 for A, which is 1.5 times 5 for the semi-minor axis. And we get 1.0626577036. And then here's 12 for the semi-major axis, which is 1.5 times 8. And what do we get? 1.0626577036. K repeats again. So it appears that, not just appears, but it happens to be the truth, that K will repeat for the ratio of A to B. And so that is an interesting thing. Why? Because even though we have been using a calculated perimeter to get to find K, we had to use an equation, a known equation for the perimeter to find K. Once we have found K, then we won't ever have to use that perimeter formula again. We can go back to calculating the perimeter from the original equation that I derived at the beginning of this work. And why is that good? Well, we're still messing with formulas, right? But the difference is that the formula that we can use once we have a table of K's, for instance, is much simpler. We can use the simple formula all the time and not have to fall back on the longer approximations or even the longer exact formula. Because if we find K from the exact formula for the perimeter of the ellipse, the complete integral of the second kind, then we will get K values that are exact, that will give that exact perimeter when used in the equation. So that is my assumption, at least. I haven't tried that, but I believe that's going to be the case. So this puts us in a position where we can develop a table of K values for ratios of semi-major axis to semi-minor axis. And then say we're writing some code that runs and finds these perimeters for us. Instead of having to use a formula to calculate the perimeter, now we can use the K value from a lookup table along with the relationship that I derived. And then we can reduce the work, especially if we have large numbers and all we have to do is look up a value of K. It would be much easier than plugging large numbers into Ramanujan's formula or the complete elliptical integrals of the second kind. So that is the value of this interesting development. It's not exactly what we were looking for, but on our journey through the universe to where we were going, we found something interesting. So let's just pick it up and keep it. What else were we planning to discuss today? Let's go back. So now that we have developed K, I wanted to move on and see if I could get an even better solution. So we're not just going to stop there. We can zero in until we get to our objective, which is to find a closed form solution built up from first principles, and in particular geometrical first principles That's what we're working with now. So what do we have? The area of the surface of this cylindrical or elliptical cylinder can only be approximated because we don't know P. P is going to always be the unknown, the perimeter, and we're trying to find that exactly. And when the cylinder has the same height as the length of its perimeter, its net diagram opens the lateral area into a square. So we have taken the formula or the search for P from the nonlinear elliptical domain into the domain of a square. And it seems that we know a bootload of information about the square. There, we studied the square inside and out. You would think that once we got the problem into that form, then we could solve it, but turns out it's still a different problem because we are facing a square with unknown sides, so we don't have any number to carry along with us, since the sides of the square are either h or p, which are set equal to each other, and both of those are equal but unknown. So recently I decided, well, let's see if we can work in this square area. So we're moving out of geometry and into topology. We're knocking on the door of a topological discussion and topological search for a solution to the problem. So one thing that I found in the research preparing to indulge in this was that if you try to make a rectangle from a line that is of a length equal to the perimeter of an ellipse, the largest rectangle you will be able to make will have the sides p over 4, and the area inside that rectangle, the square, would be p squared over 16. So that is the largest area I could make from a line the length of the perimeter of this ellipse. Since we folded it out and we're working with a square now, this perimeter is a straight line, and if we try to encircle a single square with one perimeter line, this would be the size of that square, and this would be its area. And that gave us a few more numbers to work with. We're increasing our knowledge because we've got p squared over 16 is the area, p over 4 is the length of the sides of this square, and if we wanted to find the length of the diagonal of the lateral side of the elliptical cylinder, that diagonal would be the diagonal square would equal p over 4 squared plus p over 4 squared. This would be the Pythagorean relationship between the diagonals and the sides of a square, or a triangle if we want to look at half of that square. And also we have some angles that will appear. Got the 45-degree angle on the square here in this corner. When you draw the diagonal, this corner angle, which was 90, will be broken into two angles, 45 and 45. And so we could calculate whether these relationships are reasonable by calculating the cosine of 45 degrees, which in radian measures pi over 4. And we take, that would be the cosine is the adjacent over the hypotenuse. And we know the hypotenuse of any hypotenuse of a square is the square root of 2 times that side. that would be the length of the diagonal. So we're talking about here working in this little small square whose length of sides equals the perimeter of that cylinder. P over 4, P over 4, P over 4, P over 4. 4 times P over 4 is P, which is this perimeter line. And when we calculate the cosine, we get 1 over the square root of 2, and when we make it, normalize it, we would multiply by square root of 2 over square root of 2, and we come out with the correct value for the cosine of a 45-degree angle, square root of 2 over 2. And so we got some numbers, but yet we still could not calculate P. Maybe someone else might see some other stuff that I didn't notice yet, but I could not finish it because I was distracted by my next move, which was to unconstrain the side of the elliptical cylinder to be any integer instead of just h. So we would have P and h were equal to each other, but now when we unwrap that elliptical cylinder, we will get a rectangle or possibly a square. So it will be unconstrained. It could be any integer. But we still don't know P. And now the surface area formula for an elliptical cylinder would be 2 pi AB, the top and the bottom, plus the height times the perimeter. Where now we have A, B, and H to be determined. So we've got another number to work with. We can set H to practically any number, an arbitrary value, and then see if we can find P. So the next experiment was to set H equal to 1. With H equal to 1, what do we get now? We still have an elliptical cylinder. One of the sides is still the perimeter of the lateral side, and the other side, when H is 1, will make the area of the rectangle that results when we unwrap that elliptical cylinder and form its net. The area of this lateral side is now equals P. So we got P on the longer sides, and P is the area of the cylinder. But P is still the unknown. And that is where we landed. Once we have begun this topological journey, will it be possible to crack this puzzle? Then the next thing was utterly wild. We are fully into the area of topology. So we're going to take the problem out of the domain of nonlinear mathematics and into linear mathematics, and then we're going to continue and take it into a domain that is a mixture of linear and nonlinear. So what we're going to do is divide this perimeter line here at the top into 4 equal pieces, and each one of these lines would be able to encompass 1/4 of the ellipse that it represents. So this would be the first quadrant ellipse, second quadrant ellipse, third quadrant, a portion of the ellipse, and the fourth quadrant portion of the ellipse. And each one of these quadrants would contain an area of 1/4 pi AB, 1/4 pi AB in each one of them. So this little line segment here can contain 1/4 pi AB. This line segment here can contain 1/4 pi AB, and this one the same, and this one. And meanwhile, all 4 of these line segments together, when connected into a square, will have each one have a side length of P over 4, 1/4 of the length of the perimeter. So we're combining the nonlinear and the linear into a single problem. And it is where I landed. I don't know what information we can get out of this, but all we now want is P, the value of P. And we've taken it through several different transformations of different forms, and yet we have maintained our connection to the original equation, the equation of the ellipse. Well, that's it. Thank you for joining me to hear about the interesting things that I am discovering, we are discovering about what we can and cannot do or know about the ellipse.